So, all right, welcome everybody. So today we are talking about roots and zeros of polynomial functions, and we are learning. I'm going to take a snapshot of this, and then you guys can write it down or do what you need to. This is called the fundamental theorem of algebra. So I'm not going to derive this for you, but I think perhaps you've seen this pattern developed over time. So I'll put this right here, and then we will discuss it as we need to. So the fundamental theorem of algebra, which says every polynomial equation with degree greater than 0 has at least one root in the set of complex numbers. And I just want to point out that complex numbers are numbers of the form a plus bi. So if the value of b is 0, even a real number can be considered, within the set of complex. So the fundamental theorem of algebra actually isn't all that bold of a statement itself. It's kind of weak, and it's not very definitive. Where they're basically just saying, right, so if I have my polynomial of f of x equals x to the 7th plus blah, blah, blah. They're saying, okay, because this degree is greater than 0, there's at least one root that it has, whether real or imaginary. And it's like, well, you guys could probably tell me even more. How many roots would you expect this to have? Or how many x-intercepts could you say it would have at most? 7, right, is what you guys would say. And today we're going to realize that, well, actually, even when we were just going over our midterm, it kind of covered that, which was nice, was that solving these problems sometimes have imaginary or complex answers, right? So it turns out that this will have exactly 7 roots, although some of them might be imaginary. Okay? But there is exactly 7 roots, and that's what the corollary says. Does anyone know what a corollary is? Perfect. I don't know if you guys saw corollaries in geometry or if C-O-R-O-L-L-A-R-Y. So corollary.
You look right.
Yeah. So it was a little weird. So yeah, a corollary is a follow-up to another theorem, and it's usually a short step. All right? It's like Lance Armstrong stepping onto the moon after a spaceship just brought him the whole way, right? Like he didn't walk there. Or it's like Isaac Newton saying that, in kind of all of his discoveries, he was merely standing on the shoulders of giants. Right, he just happened to see a little bit further than they did. It's that idea. The corollary is nothing without that theorem right before it. However, the corollary in this case got all the credit, all the glory. So it says a polynomial equation of the form p of x equals 0 of degree n with complex coefficients has exactly n roots in the set of complex numbers, right? So where the fundamental theorem of algebra was vague, saying, there's at least one, right? This is no, tell you what, I can one-up you fundamental theorem of algebra. There are exactly n roots, and they're all complex. So good stuff. So that means if I was referring to this f of x, we would say f of x has exactly 7 roots. Right? That doesn't mean it has to cross the x-axis 7 times, because some of those crossings could be imaginary. But there are exactly 7 answers to that problem when I set it equal to 0. Okay? So, corollary. So let's actually do an example. So what if I want to find all roots of, let's do x cubed plus 3x squared minus 10x minus 24 equals 0. So first of all, how many roots do I expect this to have?
3.
All right, because the degree is 3, we would say there are exactly 3 roots. We don't have to write it all out, but for the sake of this, that's what I'm... 3 roots. Okay? So in order to find those, we could just start plugging in values and seeing which ones give us 0 as an output. And instead of just directly substituting numbers in for x, we could synthetically substitute. All right? In previous sections, they gave us like one of the factors or one of the roots as a seed, as like a starting value. And today, we're going to just kind of start blind. All right? So let's actually just try to figure out, would -5 work? All right, my goal is actually, let me make an outline here. My goal is to kind of plug in x's and y's until I find ones that work. All right, and the ones that will work for us are the ones that will give us an output of 0. Okay, so I'm looking for ones that give me 0. And so we're kind of, at this point, just shooting in the dark. After some strategies and techniques we learn tomorrow, we will have some additional ways of narrowing it down. All right? But for now, we're just going to kind of start shooting in the dark. So if I wanted to plug in -5, what's a way I could do that? Yep, that would be direct substitution. The other way I could do is synthetic. And I'm going to try to teach us a shortcut so we can start skipping steps on synthetic, which would be nice. So when I synthetically divide, if this is a root, what do I expect to see in my answer? Right? The remainder I'm hoping will be a 0, right? If it in fact works out. Okay? But there's no guarantee that it will. And then I'll be able to, and even if the remainder isn't 0, what if this is like 7? Then what does that tell me? It tells me that, right, x plus 5 would not have been a factor. What else would it tell me? What would it tell me here? Right, that it would tell me that y is 7 when x is -5. All right, so whatever my remainder is going to be my output. So that in itself will kind of have some valuable information for us. So let's synthetically divide this. So I'd bring down the 1, multiply by -5. All right, add, multiply, add, multiply, and add. So what's my remainder? -24. Okay? So that means if I was thinking of the graph, there is a point that is left 5 and down 24. So right now that's kind of far away from the x-axis, because I'm looking for ones where it crosses the x-axis, is visually what I'm kind of doing. All right? Now, instead of having to write all of this every time, we're actually going to do a slightly different setup for synthetic division, where I'm going to kind of make a table like this. where I'll write the 1, 3, negative 10, negative 24. And then I'll put my attempts over on the side like this. And what we'll end up doing is kind of skipping some work or doing it in our heads to try to save us some space. And we'll end up getting really fast at this, which is nice. So when I do negative 5, here I did it out kind of like the long way. And now we're going to write it out the short way, where the only thing I'm going to write is this part here. Okay? So I'm not going to write the other parts. I'm going to do that part in my head. So I'll walk us through how we would do it. So let's see. The first thing that would go down is the 1. And then I would do negative 5 times 1 is negative 5. And kind of mentally, I'm thinking negative 5 up here. I wouldn't write it down, though, but that's mentally what I'm imagining. So negative 5 plus 3 is negative 2, right? So I'd write that down. So I'm kind of only writing down my answer row. Then I'd do negative 5 times negative 2 is positive 10 that I'd be imagining up there. 10 and negative 10 is 0. Right? So as a result, I'm kind of saving a lot of space and potentially some time. Negative 5 times 0 is 0, and 0 negative 24 is negative 24. And so this is still my remainder, and I see that it doesn't work out. All right, so let's try negative 4 together. So my first move is I would bring down the 1. And then I'd have negative 4 times 1 is negative 4. Plus 3, which is negative 1, right? And then negative 4 times negative 1 is positive 4. Plus the negative 10, which is negative 6, right? Because the more influential one would have been pulling it down. And negative 4 times negative 6 is... Oh. So I get a remainder of 0. So that means that negative 4 is one of my roots. Right? That an x-intercept occurs at negative 4. Right? That's what that tells us. Now technically, we also know that this is a depressed polynomial. But we're going to ignore the depressed polynomial part now, for now, just so we can keep working through this in this fashion for now. But we would normally be able to use the depressed polynomial to kind of save us some time. So let's plug in some other values here. So let's try negative 3, negative 2, negative 1, 0, 1, and let's see if we can pick up the speed here. I'll do one more with us as class, and then we'll have you guys try the rest here. So let's see, I'm bringing down the 1, 3, 0. Negative 3 times 0 is 0. With a negative 10, it's negative 10. And that's positive 30. So that's 6. And also, normally I wouldn't be writing this table of values. I just kind of wanted to have it there so you kind of see, make that connection in your brain. Like, also, this is representing a table of values. And I could also plot all of these points if I wanted, if I was working on a graph, right? Stuff like that. So yeah, let's have, so this one, I just want to point out, negative 3 is not a root. How did I know? Right, because 6 was the remainder. If that was 0, it would have worked, but it doesn't. So let's have you guys try some other values. And how many more roots do I expect to find? There should be 2 more somewhere in there. Let's have you guys take it away, Squidwards. Count it down the sunset. It takes a little bit of adjusting, getting used to writing synthetic division without those other steps. Let's see how much further we got to go here. On the hunt for the last root. Let's see, 6, 8. Found it. So don't only just check your answers, but also just give a quick look, make sure that all of your work lined up as well. Which theoretically, I mean, you wouldn't have been getting the right answers without the right work, but who knows what coincidences could occur. So I found all 3 of my roots, which would coincide to the x-intercepts of the graph if I was graphing this problem. And some of the things that I want to point out to you is that you can do some additional kind of interpretation of what's going on here. Is just like we were analyzing tables in the last section we did, I just want to point out, kind of imagine what's going on with like the swoops of the graph here. Right, so here it's negative 24, and then it goes up to 0, up to 6, down to 0, down to 12, down to 24. And so like when I got here, I got a little bit worried because I was like, man, I'm going down, right? Like that's getting further from zeros, right? If I'm negative and I'm getting, more negative. And then this is down again, and I was like, I actually was considering just skipping plugging in 2. Just to try to guess one a little bit further out, because I figured it would take a little while for it to loop back. And then I saw it went up, and I was like, okay, all right, I'll keep going. So I just want to point out that, you can actually kind of visualize, like, all right, it's down underneath 0. Oh, it's approaching it again. And if, for instance, let's say I didn't find a root, but I saw that it went from, well, actually, that's not a good case. Well, let's imagine. If this went from negative 12 to positive 24, what could you tell me occurred in between there? If it did. Yeah, right? If it passed from a negative to a positive, I would know that it must have crossed the x-axis in there, and that I would need to start guessing points in between there. All right, is what we would consider. So if I did end up deciding to like skip 2 and 3, and then I tried 4, and 4 was some positive number, and my last attempt was like negative, I'd realize, I jumped too far. I might need to try some a little bit earlier. And then the other thing I want to point out is that not only do we have that analysis, but once I find one, I actually can do the same chart, but with a depressed polynomial. Now, the only thing to be cautious of is that with the depressed polynomial, keep in mind that all of the points that I'll be getting, if I try a depressed one, will not line up with these. The only points that they have in common will be the x-intercepts. Okay? So it's okay to work with the depressed polynomial. So I could have, as an alternative, once I found this, I could have been like, okay, now I'm going to make an entirely new chart where I'm plugging in 1, negative 1, 6, and now let's try negative 3 and negative 2. And just for sake of example, I'll show you that negative 2 will still line up for us, right? Because it worked on this one. It should also work for the depressed one. So let's see, I'll try negative 3 first. So 1, negative 3, negative 4, and then that'd be...
That's a negative.
Is that a negative? Wait. Oh yeah, good call. Thank you. You guys always get my back. Let's see. Yeah, negative 1, negative 6. Good. So let's see, bring down the 1, negative 3, that's negative 4. It'd be positive 12, and negative 6 is positive 6. So I'd say, oh, that's too high. And then I try negative 2. So bring down the 1, negative 2 is negative 3. Negative 2 times negative 3 is positive 6. With a negative 6 is 0. So notice that negative 2, even if I worked with a depressed polynomial here, which it saves me a whole column of work, right? Once I have it depressed, it would chop off one column, and then I'd have only 3 to try. And then if I found another depressed, which actually I guess I can, here's an even more depressed polynomial. I could then try it with just 1 and negative 3. And then I could try some other ones, right? Try negative 1, 0, 1. And then it would work once I hit 3 again. And just to verify that it works for 3, check this out. Bring down the 1. 3 times 1 is 3. And bam, it would even work there. So I just want to point out you could even save more time for yourself working with depressed polynomials. All right? Just be aware that this 6 does not line up with, oh wait, what? All right, well that's a coincidence. Man, that so didn't help me prove my point at all. Thanks a lot, math. Ugh. So yeah, the depressed polynomial may only coincide with your function at the x-intercept. So don't expect to be able to graph it based off of the other information. All right. So like if I plugged in negative 1 here, I'd have 1, negative 1, and negative 3 is negative 4. And notice when I plugged in negative 1 here, I had negative 12, not negative 4, right? So there's an example of a number. And it's more likely that it won't line up with your original than that it will. But if all we're looking for is the roots, it lines up in all the places I care about. So that's fine too. So if I was using the depressed polynomials, I wouldn't have been able to use any other information about my graph, but it still would be saving us time. Okay, so there are weaknesses to this strategy. Like, what if my roots ended up having to be at like negative 22, or 1,071?
That would take a really long time.
Yeah, or what if it occurred at like 1.729138 times the square root of 41? I realized the square root of 4 would have reduced, so that wouldn't have been very helpful.
Could you skip and go up by a certain amount of numbers and then figure out where it would have processed intercept and then create like an inequality type thing?
Well, yeah, like if I could skip around and then when I realized the sign changed, right, I could realize, there might have been a root in between there. But even that, you have to be cautious. Because imagine I've got a graph like this, and what if I've got like this? And what if I see like this is going up over here, and I'm like, okay, I'm going to skip ahead for a little bit. But what if I skipped so far ahead that I skipped all over to this point, and I'm like, aha, there's an x-intercept between here and here, but maybe there's like 3 or something, or what if I skipped ahead and ended up being like right here, and I'm like, okay, I guess I can keep going because there's no x-intercepts between here and here because it was negative the whole time. So we do have to be aware, like maybe your graph was a little bit quicker at the turnaround than you expected, so stuff to be aware of, but all sorts of analysis that can be helpful. And now instead of picking from infinitely many numbers, we will learn a strategy tomorrow that will at least narrow it down for us. And then the other thing is, once I had this, I might as well make this other connection. Once I found the first one in this case, my depressed polynomial was x squared minus x minus 6, right? And this I know how to factor, or at least I know how to solve a quadratic. So I mean, if I had in this case I had a third degree, so once I found one root, my depressed polynomial would be a second degree, and I could find those other two using quadratic formula, completing the square, or factoring. If this was a 7th degree, I'd have to find a few more before I could work with a depressed polynomial that I'd be able to find the others more quickly. And I just want to point out that this does happen to factor to be, what was that? That would be x with 2 and x with a 3. And the 3 is negative. So I'd end up getting x equals negative 2 and x equals positive 3, which are the roots that I ended up finding, right? Negative 2 and positive 3. So you can still use some of your depressed polynomial tricks. Once you hit a quadratic, you probably shouldn't keep searching through the table, right? We could probably narrow it down and, use our factoring techniques or something like that. So that's the idea for how those will work. But now there's one more thing I want to point out. Actually, that's what I want to do. Blah, 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 blah. Tomorrow we'll do this little Descartes' rule of signs. But I mispronounce his name intentionally all the time. I think it's Descartes. Actually, wait, you take French. How would you say Descartes? Descartes, right? Wow, man, you said that awesome. I never could do that.
I don't speak French too.
Yeah. So I'll intentionally just butcher his name. I'll say Descartes. Or like, I don't know. I'll just really mess it up. But it's fine. It's his mathematical principles we care about anyway. Let's do a consider problem. Solve x squared plus, let's do 9 equals 0. All right. So how many x-intercepts or roots do we expect this problem to have? 2. As a matter of fact, according to the corollary of the fundamental theorem of algebra, we know there's exactly 2. All right? We know that. So let's solve this. And notice, right, in this case, since there's no b term, I don't have to try factoring techniques. I can actually just get x by itself. And then I could do what? Root, plus or minus, don't forget it, right? And I would get x equals plus or minus 3i. So I end up with 2 roots, both of which are imaginary. And it turns out that those imaginary roots, in this case, are opposites of each other. But it turns out, note, when we've had imaginary roots in the past, they have always been conjugates. All right, even when we were just solving a problem on the midterm earlier, like if I had 2 plus 7i as a root, then we also had 2 minus 7i as a root, right? Because I would end up, like I think I had an answer like this where I had like 3 plus or minus, what was it, like I square roots of 6 over something, right? There are 2 roots here, and they happen to be conjugates of one another, all right? Those 2 roots would have been 3 plus the square root of 6 over 2 times I, and 3 minus the square root of 6 over 2 times I. So notice that these 2 are conjugates. So it turns out that the complex conjugates theorem tells us that when you have one imaginary root, you will have another imaginary root that's the conjugate of it. So I'm going to just grab a quick snapshot of that. And let's see, that summarizes it. Complex conjugates theorem. There, that's good enough. And I think I'll have to fit it up at the top of the page, sadly. So this is the last theorem we're doing today, but we'll do an example or 2 with it. So it says, suppose a and b are real numbers with b not equal to 0. If a plus bi is a 0 of a polynomial function, then a minus bi is also a 0 of the function.
I just spelled function without the C.
So the way I think about this, or the little way I remember it, is if you have an imaginary friend, it turns out you also have like an imaginary enemy that tells you to burn things.
That was like
Yeah. Yeah. Don't have imaginary friends because there's always an evil one as well.
I'm talking so much imaginary.
Uh-oh. Ay, ay, ay. Al más terrible del mundo. So let's see. So let's do, there's a couple concepts showing up in this problem, but that's fine. So I'll do another third degree function. That exponent suddenly got far away from its base. X squared minus 7x plus 51. Ugh. And then if 4 minus I is a 0. So for this polynomial, they've given us a hint. All right, they're saying, all right, we happen to know that 4 minus I is a 0 of this function. Okay, so if 4 minus I is a 0, then 4 plus I is also a 0. All right, so let's see, for this function, so I guess, so zeros, so first of all, we know there's 3, right? There's 3 of them. We know that 4 minus I is a 0, and you guys, by the complex conjugates theorem, just verified that 4 plus I would also be a 0. And then there's one more that I'm looking for. Now, question, this one's maybe a little bit abstract because we're just getting used to this idea. Could this other 0 also be imaginary? Right. Because if this one's imaginary, let's say this was like, I don't know, 5 plus I, that can't be the case because we just learned that they come in pairs because then 5 minus I would also have to be 1, right? So we know that this one cannot be imaginary, all right? Because I know that there was a total of 3, all right? The other thing that I know is that, graphically speaking, this is really kind of pulling it back to what we did a while ago. All right, this is a third degree function. If it's got 2 imaginary roots, right, just based off of the end behavior, it's probably something like this, but there's no way for it to have all 3 imaginary roots because odd degree functions have end behavior in opposite directions, and at some point, they will have to cross that x-axis, all right? There's no way to teleport or to, like, jump to the other side. So I do know that this one's going to be real, all right, for both of those reasons that we just stated. So in order to find that, this is kind of an interesting strategy. We are going to, let's try to find the least confusing way to say this. Let's find the depressed polynomial that has these 2 imaginary roots. And let's see, I think it was the factor theorem that said if a is a root, then x minus a is a factor. Right? So don't write this down. But if 2 was a root, then you would say x minus 2 is a factor. If negative 5 was a root, you'd say x plus 5 was a factor of the polynomial, right? You guys remember that? Or at least recognize that pattern? So it turns out that this factor theorem also applies in the case of complex numbers. So if a is 4 minus I, then let's see. I think I've been working with green for my g's of x. G of x, that means a factor will be x minus 4 minus I. Kind of weird looking, but let's be cool. It'll be all right. All right, because this is my a, so therefore x minus a is a factor by the factor theorem. And if 4 plus I is a factor, is a 0, then what also must be a factor? X minus 4 plus I, which, yeah, it's technically going to simplify out. So this is going to be some depressed polynomial that happens to have these two as its roots. Now, how is that going to help us? I know whatever this is going to be a factor of the original polynomial. And if I want to find the remaining factor, I could actually divide the original by this depressed, and it will give me the remaining x minus a factor that will give me its root. So it's kind of like a lot of concepts pulling together here. So we'll walk through it, and hopefully we'll be okay. So in this current form, this isn't very helpful to us. So let's distribute these minus signs, why don't we? So I'll have x minus 4 plus I and x minus 4 minus I. Right? If I just distribute those minus signs, it just opposited all of the things in the mini parentheses. I don't know if opposited is a word or a verb, but I just did that. And now I've got kind of like a trinomial times a trinomial. They're not technically that, but if I want to multiply these out, I can actually do distribution. So I'm going to end up having a very long thing with 9 terms in it. Okay, so leave some space. Try to fit it horizontally on your page. And let me just show you kind of the general idea of what I'm going to be doing here. So I'm going to multiply this x times all 3, right? Then I'm going to multiply the, let's see, I guess I'll use yellow, the negative 4 times all 3. And then I'll end up multiplying the, let's see, I'm running out of good colors here. And then I'll multiply the I times all 3. All right, so I'm triple distributing. Distributing. That might have worked out. Yeah. So x times x is x squared. X times negative 4 is negative 4x. And x times negative I is negative x. And now I'll distribute the negative 4. So that's negative 4x. Negative 4 times negative 4 is plus 8. And negative 4 times negative I is?
Wait, negative 4 plus 16.
Thank you. Wow. Man, where would I be without you guys? Plus 16. I was so focused on the sign changing, I just did the multiplication wrong. And negative 4 times negative I is positive 4i. It's all right. This thing is going to be beautiful when it's done. I promise. And let's see. Now I'm distributing the I. I'm doing the blue distribution here. I times x is plus x. I times negative 4 is minus 4i. And I times negative I is negative I squared. Yeah, isn't it wonderful? This is like my favorite part. It's like playing Fruit Ninja here. Ready? Here we go. We're just going to go swipe, 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 like all over the place. So let's see. What cancels out?
Negative 4i.
Negative 4i and positive 4i. Yeah, I guess I wish there was more, but it felt like a lot in the moment there. And then I can combine some like terms where I've got negative 4x and negative 4x. That will be, let's see, so I'll have g of x equals x squared minus 8x. And then, does anyone know what we could do with this I squared? I squared is equal to negative 1, right? So negative I squared is plus 1. So I can combine 16 and plus 1 to get 17. Yep, because it's minus the negative 1. Yeah, technically I should show a little bit more work in there, but I'm trying to shorten an already long problem. Okay, so now I've just found the depressed polynomial. Next I'm going to long divide our original function by our depressed function to get another depressed poly that contains the remaining factors. Okay, so what I'm going to do is, and unfortunately this will have to be long division because I'm dividing by a trinomial here. I think we'll just have enough time to do the setup here because the bell's about to ring. Let's see, let me see. I'm going to grab x cubed minus 5 minus 7 plus 51. So when I do all of this out, I'll end up getting an answer of some other depressed polynomial. Okay? After doing that all out. And then the last part will be set h of x equal to 0 and solve. Okay? So I think we're just about out of time, so I'm going to have to end the stream. But at least this is laid out. Not all of them tonight are going to be this tricky, so do not fret. Actually, I might just keep going with things. You guys have your homework. I might just finish recording this lesson so it'll at least be right online, and we can talk tomorrow. So I'm just going to be talking to myself for a little bit. You guys pack up. Make sure you get out of here on time. So let's see. So h of x... I'll end up cheating here. Ends up equaling x plus 3. So to solve, I'll set x plus 3 equal to 0, and I get x equals negative 3 as my remaining 0. So my 3 zeros end up being 4 minus I, 4 plus I, and negative 3. And those are all 3 of the zeros. Right? So this negative 3 came from my h of x little depressed polynomial. All right. So I'll talk to you guys later.